Cool. Okay, cool. So thanks for coming to the Proof Complexity workshop, everybody. It's really fun to be able to organize this, and I'm glad to see that we have lots of participants. So yeah, so the goal of this workshop is to kind of outline some of the exciting recent progress that's been going on in propositional proof complexity. So in the past 10 years, we've seen sort of a lot of progress on multiple fronts in proof complexity. And the talks in this program are kind of chosen to sort of illustrate the different areas, and in particular, the connections that proof complexity has with other areas of theoretical computer science. So starting off the workshop today, we're going to have Toni Pitassi and Josh Grochow talking about algebraic proof complexity and the connections with algebraic circuits. So yeah, both of the speakers have done sort of many of the landmark results in algebraic complexity. So together they introduced this the ideal proof system, which is very closely related to the VP versus VNP problem. Tony's responsible for introducing and analyzing some of the original algebraic proof systems in the 90s. So we're really excited to have them open up our conference. So yeah, so I'll stop sharing my screen, and maybe if Tony's ready, we can take it away. Perfect.
Okay, can you see see the screen so far?
Yep.
Okay, hold on. All right, I think we're good. You can see that, right?
Yep, perfect.
Okay, perfect. Just give me 1 second. Okay, thanks everybody. Yeah, sorry about hopefully there won't be any more technical glitches. Yeah, so this is just meant to be a prologue or of algebraic proof complexity. This whole session is on algebraic proof complexity, and I'll talk for, I don't know, a little over half an hour, and then Josh will talk. So I'm going to kind of give the prologue. If you have any questions that are really kind of urgent to have answered, please go ahead and ask it in the chat, and I'll address it. Otherwise, we'll hold off on the questions until after. Okay. Yeah, so part 2 will be Josh right after me. Okay, so one of the, some of the main questions here is, about algebraic complexity is really in general about proof complexity is what's the difference between circuit bounds and proof complexity bounds. And in particular, why are we not able to prove lower bounds for bounded depth Frege proofs, despite the fact that we've had the corresponding circuit bounds for many, many years? So let me just start with reminding you what the basic goal is of proof complexity. So the input is a formula over some set of Boolean variables, x1 through xn, and the satisfiability problem we want to output sat if there's an assignment that satisfies the formula, and unsat otherwise. And proof complexity is about trying to understand how hard it is to certify or prove that a particular unsatisfiable formula is unsatisfiable. So I'm not even going to define Frege proofs, but essentially they're it's a system of rules. So you have an underlying set of connectives, typically and or a negation. And a proof is sort of it's a directed acyclic graph, where if we want to refute a formula F that's unsatisfiable, we have at the top, let's see if I can even use let's see if this works. Can you see this, my pointer?
Yep, I can see it.
Okay, great. So at the top of the proof, we have the unset formula F that we're trying to refute, together with instances of axioms of the underlying Frege system. And you're allowed to derive new formulas or new formulas from previous ones by applying one of the inference rules of the Frege system. And the goal is to derive the identically false formula, which is, say x and not x, or the formula 0. And the size of a proof is just the sum of the sizes of all the formulas in the proof. And loosely speaking, we can talk about C Frege proofs, where C is a particular circuit class, and that's a Frege proof with a restriction that all of the lines in the proof have to be functions that are in that circuit class C. So, for example, and when we restrict the circuit class C to be just disjunctions, we get resolution. And if C is AC0 circuits, we get AC0 Frege, and so on. Ordinary Frege systems, the lines are formulas, so NC1 circuits. And extended Frege refers to the Frege systems where the lines are ordinary circuits, call them P/poly. And the goal of lower bounds is to show that there's, for increasingly stronger proof systems, that there's a sequence of unsatisfiable formulas that requires exponential length proofs as we go up this hierarchy. But at the moment, we're really quite stuck, and have been for a very long time. We haven't been able to break through this barrier. We have lower bounds for bounded depth Frege proofs, using a lot of tools that were, such as the switching lemma, plus new tools that were used to prove parity lower bounds for AC0 circuits. A lot of those tools were used and generalized in order to prove AC0 Frege bounds, for example, for the pigeonhole principle or for random formulas. But once we add mod P gates to the bounded depth circuits and allow the lines to be bounded depth circuits with mod 2 gates, say, then we have no lower bounds whatsoever, despite the fact that we've had Rasbroff-Smolenski prove the analogous circuit lower bound result back in the 80s. So, why is this so hard? And not only do we're not able to prove lower bounds for AC0P Frege proofs, but we can't even prove conditional lower bounds. We can't even prove that some circuit lower bound assumption implies AC0P Frege lower bounds. And conversely, if it seems so hard, you would think that we should be able to prove a result in the other direction, that AC0 Frege bounds implies some circuit bound or implies something, something surprising. And we don't really have any results along these lines. So this sort of motivated the study of algebraic proofs, which began, I guess, in the 90s. And the idea here was to, the same way that, it's hard to make progress on proving superpolynomial lower bounds for Boolean circuits, but maybe if you move to the algebraic setting, which is more syntactic, you want to prove that no small algebraic circuit can compute a particular fixed polynomial, which seems like it's a necessary step toward proving Boolean circuit bounds. So similarly here, we thought that maybe by studying algebraic proof systems, it would be a way eventually to prove Frege lower bounds, and also give us a whole new class of techniques coming from algebra representation theory and so on. Okay, so let me introduce the corresponding NP complete problem, or co-NP complete problem, which is in the algebraic setting. So the input is a system of polynomial equations, P1 up through Pm, where each of these, think of it as a low degree polynomial over variables x1 through xn. And we say that the system of polynomial equations over a field, or think of F as being an algebraically closed field typically, we say that this system is unsolvable if and only if there's no assignment to the variables over the field that satisfies all the equations. So we want to output 1 if it's solvable and 0 if it's not. And this is just another. We can think of this as another way to think of SAT, because if we have a K-SAT formula, C consisting of clauses C1 up through Cm, we can convert the clauses to corresponding polynomials. And here's an example. So here's an example. This clause here converts to this polynomial. And the conversion has the property that a particular assignment satisfies this. If a particular assignment alpha, a Boolean assignment, satisfies this clause, then plugging in the same assignment will set this polynomial to 0. And additionally, we'll add these equations that force all the variables to have values either 0 or 1. So this is how we can convert the question of whether or not a CNF formula is satisfiable to the corresponding question about whether this corresponding system of polynomial equations on the right is solvable. And we'll mostly, when we want to relate when we want to relate the algebraic proof systems to the propositional proof systems, we'll really be interested in polynomials that are coming from CNFs, and so we'll call those CNF systems. Okay, so a classic theorem in algebraic geometry, this is a particular refutational version of it, a baby version of it. Hilbert's null-stone set states that if you have a system of polynomials, then it has no solution over an algebraically closed field if and only if one is in the ideal generated by these polynomials. Or in other words, if there exists polynomials q1 through qm such that the sum of the qi's times the pi's is identically 1. And then we'll consider these qi's to be, we'll call it a null-Stahlensatz's or NSAT's proof of unsolvability of the polynomials p. The complexity of a proof is the maximal degree of all of the QIs, and we can also measure monomial size. So the total sum of all the monomials and all the QIs would be the monomial size of the proof. And when these QIs are, when they're CNF polynomial systems, so coming from CNFs, then these QIs will be multilinear without loss of generality because we have those extra equations that force the variables to be 0, 1, the xi squared minus xi equals 0. So the QIs are multilinear. And so the largest degree that you could have is n basically. And then the size, the biggest, the trivial size of any refutation for CNFs would be exponential in n. And polynomial calculus is a generalization of null-Stahlensatz's where the degree is measured more dynamically. But I won't talk too much about that today. Okay. And then, so that's null-Stahlensatz's, which we view as a refutation system for a system of polynomial equations. And there's a version of null-Stahlensatz's for in the semi-algebraic setting as well, which is called the positive Stahlensatz's. Again, this is the refutational version. Now we have a system P of polynomial inequalities. And the theorem states that P is unsolvable over the rationals if and only if there exists sum of squares polynomials Q sub L, where L is in 0, 1 to the M, so that the sum of the QLs times the PI's raised to the power Li is -1. So again, we can think now of these QLs as a refutation of the corresponding polynomial inequalities, and we'll call these QLs an SOS proof or SOS refutation that P is unsolvable. And again, when P is a CNF system of equations, then we can assume things are multilinear. And again, we can measure the complexity here by the maximal degree of the QLs or by monomial size. So these proof systems were defined quite a while ago. And in the 90s and 2000s, there was a lot of really nice work proving optimal linear lower bounds on the degree of many important unsatisfiable system instances, such as the pigeonhole principle, random KCNFs, random KXOR, planted clique, etc. And these turned out to be amazingly useful. And I'm focusing mostly on SOS here, but same thing's true for null-Stahlensatz's and polynomial calculus. So first of all, why are lower bounds for SOS and null-Stahlensatz's so useful? Well, the mantra here is that lower bounds actually for SOS on the degree of SOS refutations for for a certain family of unsolvable CNF polynomial equations, lower bounds actually imply lower bounds for a broad class of algorithms. And here's some examples. In Raghavendra in 2008 proved, roughly speaking, that under the unique games conjecture, it holds that for every CSP instance delta, the optimal polytime approximation factor for delta is actually the best provable one, the best one that's provable in constant degree SOS. So lower bounds on constant degree SOS reputations for delta tell us that, lower bounds for a particular type of statement give us inapproximability results for polytime algorithms under unique games. Another example is the linear programming SDP extension complexity of a particular problem. And these papers, the LRS in 2015 and 2016, showed a connection between the extension complexity of the problem and the Shirley-Adams or SOS degree of the corresponding system of polynomial equations. This is a hard theorem, but nonetheless, the extension complexity reduces to the SOS degree of a corresponding system of polynomials. Another example is a result by Robert Robert, myself, Ben Rossman, and Steve Cook, and then later papers by myself and Robert in his thesis, where we show that monotone formula size and monotone span program size can be captured by null Stalin-Sutz degree of a corresponding system of polynomials. And GGKS showed a similar thing for monotone circuit size, that it can be characterized roughly by polynomial calculus degree, and in fact, resolution degree, which is a special case of polynomial calculus degree. So SOS lower bounds have been extremely useful for understanding large classes of algorithms and large classes of circuits and algorithms for solving and approximating problems. Maybe what's more surprising is that upper bounds, SOS upper bounds, so showing that certain systems of polynomial equations have low degree proofs, they actually have been used to get new algorithms. And the mantra here is that upper bounds can sometimes automatically actually generate efficient algorithms. And the reason is that these systems, polynomial calculus, Shirley-Adams, SOS, they're automatizable. What that means is that if there's a degree D refutation in one of these systems, you can find it. There's an algorithm that finds it in runtime n to the D. So if you have a constant degree refutation of a system of polynomials, this algorithm will find it in polynomial time. And therefore, if you have a low, roughly speaking, if you have a low degree proof certifying just the existence of a solution to some problem, you applying the automatizability, you automatically get a polynomial time algorithm for finding the solution. And this high level idea has been used, looking underneath the hood to get really improved lower bounds for a wide variety of average case problems like dictionary learning, tensor completion, and so on. Okay, so these very low level algebraic proof systems have been really quite useful and led to all sorts of really nice results. But what does this have to do with Frege bounds, which was one of the original motivations for switching over to the algebraic systems? So unfortunately, these systems that we're talking about, polynomial calculus and SOS, they're actually pretty weak. So the corresponding circuit class C is just low degree polynomials, because all the lines in the refutation are either low degree polynomial equalities or low degree polynomial inequalities. So they're not really strong enough systems to efficiently simulate Frege systems or even bounded depth Frege systems. So what we want to do is generalize these systems by, instead of measuring the complexity of the proof of the QIs by the number of monomials or by the degree, we want to measure the complexity by the algebraic circuit size of the QIs. Okay, and doing this, we can generalize the algebraic systems for unsolvability of polynomial equations. We can generalize it to get the proof system IPS, and generalizing the semi-algebraic system SOS, we get the cone proof system defined by Alexey Grigoriev, Hirsch, and Semeret in 2020. Okay. So I'm just going to talk about it, just talk about IPS, which generalizes null sets in polynomial calculus. So here's a picture of a refutation of some family of polynomial equations, P1, P2, etc. This is the proof. So you multiply P1 by Q1, P2 by Q2, and so on. But in IPS, we don't want to measure this by, the sum of the sizes of the monomials. Instead, we want to come up with the most compact algebraic circuit for computing Q1. And down in this picture here, this is, let's see where, this is it, okay? And then we multiply that by P1, and then again, come up with the most compact representation of Q2, and we can reuse parts subcircuits that we had for this. So here, this subcircuit here computes Q2. We multiply that by P2, finally add it all together to get 1. So we think of IPS as just a single algebraic circuit that takes as input the variables and the PIs, and should generate, and it should be computing the identically one polynomial. Okay. So we can think of this, so that it was defined sort of in this way in these earlier papers that I wrote. And in this later paper with Josh, we have a nicer formulation of it, where instead of we can think of this refutation as just a single circuit C with two types of variables: the X variables plus new placeholder Y variables, where Y1 we'll think of as a variable that's a placeholder for P1, Y2 is a placeholder for P2, and so on. And the single circuit should satisfy these two properties. First, when you plug in the original polynomials for the y's, you get the identically one polynomial. And number two, when you plug in zeros for the y's, you get 0, the identical 0 polynomial. And these two conditions together tell us that 1 is in the ideal generated by the PIs. And now the proof size is just the size of the circuit C that satisfies these two properties. Okay, so the crucial fact here is that proofs in the Boolean setting, they were kind of complicated semantic objects, complicated syntactic objects. So they didn't have too much semantic meaning. And when you try to assign semantic meaning to them in the obvious way, it just leads to trivialities. In this case, proofs in IPS, proofs here are now ordinary algebraic circuits, so they're kind of less syntactic, and they're just algebraic circuits that satisfy two particular properties, namely these two properties, 1 and 2. And these two properties are both polynomial identity tests, so they can both be verified in randomized polynomial time. And because of this, because proofs are just ordinary circuits satisfying two PIT tests, we were able to show for the first time that a proof system lower bound, in particular superpolynomial IPS lower bounds, imply algebraic circuit bounds, in particular implies that VP doesn't equal VNP. And at the same time, IPS simulates Frege systems for unset CNFs. So if we could prove lower bounds for IPS for unset CNFs, that would imply superpolynomial. If we could prove superpolynomial IPS lower bounds for unset CNFs, that would imply superpolynomial Frege bounds. So this theorem states that IPS simulates extended Frege, and the formula version of it simulates Frege, and constant depth version of it simulates over the appropriate field, which would be the field mod P, efficiently simulates AC0P Frege. So that means, like I said a minute ago, that lower bounds for CNF systems gives Frege bounds, and even in constant depth bounds for CNFs would solve the problem that we've been stuck on for a very long time. Does anybody have any questions? I can't.
Yeah, there was one question in the chat there.
Yeah, so basically back when you're talking about the upper bounds for SOS being helpful, I was wondering so you mentioned, so how general is it? Because you mentioned, that there are the upper bounds, it can get an algorithm and get actual algorithms to the original problem. Is this like true? Like no matter what, if you get an upper bound, you can get this. Is it only like, is it depend on what the original problem is, or how does it depend on that?
No, it definitely depends on the original problem, and it depends on the formulation. So at a high level, the unset system of equations would say, so if you have, I don't know, an instance of, say, vertex cover, and you want to show, you want to study like how hard it is to approximate vertex cover, you would write down a system of polynomial for a particular instance that you think is maybe hard. You'd write down a system of polynomial equations saying that, that this has, that this has a solution, that there is a vertex cover of a certain size. And if you can show that that's hard to prove in SOS, then hard to refute in SOS, then that kind of, shows lower bounds. If you can show that it's easy to refute, if it has, if you can show that it does have an SOS derivation, then it means that SOS can verify that it has, that it does have that solution, and then by the automatizability, you would get an actual polytime algorithm for finding that approximation factor. Does that roughly make sense? But there's a lot of caveats. There's a lot of caveats, and to get interesting results, usually you have to kind of go under the hood and actually look at the look at a little more than just the proof, the SOS proof.
I see. So you have to do a lot more work. It's really good stuff, but you have to do a lot of work. I see.
Well, you can. Okay. I mean, what I'm saying. You don't need to do a lot of work, but to get a good result, to get a good to get a good algorithm for it hasn't been found before.
Okay, I see. Yeah,
but
that makes sense. Awesome.
The intuition is definitely the original intuition is definitely still coming from understanding how to just prove that there exists a solution of that quality. And if you can formulate that upper bound in SOS in low degree, that does automatically give you an algorithm.
I see. Awesome.
I'm just pointing out that all these papers didn't just like do nothing.
Right. Of course. All right. Awesome. Thank you.
Sure.
And Tony, just saying you have 5 minutes.
Yeah, I realized I went faster than I thought, so that's why I thought I'd take a question if there was any. Okay, so this is kind of my last point. What do we know about IPS in terms of lower bounds so far? And there's actually been a lot of really exciting progress since Josh and my paper. The first paper by Forge, Boca, Samaret, and Vigderson proved they basically ported lots of tools from algebraic circuit complexity to obtain lower bounds for subsystems of IPS, the low depth case, the multilinear case. Not just tools, but they imported like important ideas and also posed some nice new problems and new ways of thinking of things, as did my original paper with Josh. In 2020, a really interesting paper showed that under a certain assumption, Shub-Smale conjecture or the Tau conjecture, that implies superpolynomial IPS lower bounds. And then another really exciting paper by Alex Sieve in 2021 proved unconditional lower bounds for a strong subsystem of IPS, but the measure of complexity is bit complexity as opposed to like number of lines. So the measure of complexity is a little bit too weak to give true IPS lower bounds. And then quite recently, a really exciting paper by Andrews and Forbes pretty much solved the problem. So that, but with a caveat, so they proved quasi-polynomial lower bounds for constant depth IPS using the breakthrough new results proving constant depth lower bounds for algebraic circuits over the rationals. So leveraging that result plus a lot of new machinery, they were able to prove similar quasi-polynomial lower bounds over the rationals for constant depth IPS. So super excited. There's caveats in all of these, but I don't want to, probably too early to get into all of that. But the one caveat I do want to mention, well, first of all, a lot of them are over the rationals instead of a finite field, but a bigger issue, I think, is that the hard systems of equations for all of these, they're not Boolean, they're not CNF formulas, and if you try to convert them to CNF or even just arbitrary Boolean formulas, the process of converting it will make you lose the lower bound. So while these results are really great in the algebraic setting, they don't yet port over to say anything about the Boolean setting. So they don't imply any kind of Frege bounds or AC0 mod T Frege bounds yet. But what do we have for CNF lower bounds? We do have some progress for IPS lower bounds for CNFs. It's again, the scale is different. So these results here, all of them are dealing at least with some, at least like depth 2 IPS. So a much reasonably strong subsystems of IPS. Here, we're kind of really down low. So we've had lower bounds for polynomial calculus and null cell sets for a very long time. And what I noticed with Russell and Pagliazzo and Sasank-Mooley is that these earlier lower bounds, they break quite easily, even under just simple linear transformations. So linear, like have a new variable y1 that's some linear, this alpha times x1 plus beta. So just a simple linear transformation, a simple change of basis, the earlier lower bounds broke. And so we posed the question of getting lower bounds under linear transformations, and Sokolov in 2021 managed to do this. He proved polynomial calculus or lower bounds for polynomial calculus for random CNFs, even with these linear extensions. So even with the even with the new variables, it allows this linear transformation. And this can be viewed as a very kind of, so once you add some kind of extension axiom, then you're getting a little bit higher up in the IPS setting. You're like almost depth, you're somewhere between depth 1 and depth 2 IPS. And in a quite recent result with Russell and Sasank-Mooley, a PhD student at UCSD, we generalized Sokolov's result to prove lower bounds where the extension axioms there can be a linear number, and they're more general than this. So they can have arbitrary, these don't even have to be linear, and as long as the support size is little O of n. So you can have arbitrary, but a relatively small number of extension axioms where each yi depends on some little O of n many previous variables. So it's a significant generalization of Sokolov's result. On the other hand, it's still not even depth 2 IPS, but it is for CNF. Okay, just to end, Josh will be talking a lot more about some of these things and getting into more details, but some high-level open problems. How strong are these systems, IPS and the cone proof system? What is the weakest system that can simulate them? We don't know the answer to that. And a really interesting question is whether extended Frege can polynomially simulate IPS. And it's interesting because it's really closely connected to polynomial identity testing. Like I said before, we have these really nice lower bounds for IPS, but they don't, most of the really strong ones don't work for the Boolean setting. So can we strengthen those? Yeah, and then later on in the workshop, we'll hear a session on witnessing theorems in TF-NP classes that correspond to proof systems. And this question is about whether we can come up with similar TF-NP classes that correspond to algebraic proof systems. Yeah, and that's basically it. And I'm pretty much on time, I think, almost. Thank you.
Great, thanks, Toni. Maybe while Josh sets up, we can answer a question if there's any. No, none. I have one quick question, which is like, so these polynomial systems, are they like, so like in a lot of other algebraic lower bounds and semi-algebraic lower bounds, there's like a lot of them come from considering things like knapsack tautologies. Is it something similar for the recent breakthrough things in IPS?
Yeah, so the first ones, a common one is, maybe you'll remember the name of it, bit complexity. It's like subset sum, it's like knapsack. So what's nice about it is that it's simple looking. It's like the sum of a bunch of variables times some constants equals something. For the last one, the strong one that I mentioned by Andrews and Forbes, it's different than that. It's actually really interesting. So it's basically stating that if you have a matrix, it's sort of saying that if you have two matrices A and B, that if A times B is the identity matrix, then B times A is also the identity matrix. But it's not that good. Instead of saying B times A is the identity matrix, you say the determinant of A is 0.
Oh, I see.
And
Right.
so the problem with that is to say that to express the determinant as a circuit, it'll end up having poly size and log depth. So the inputs to the IPS proof is really quite big and deep compared to what we're allowing the proof to do. We're only allowed the proof to do constant depth.
Right. I see.
Stuff. Yeah, but still very interesting. Unsolvable equations.
Right. Yeah. So Josh, if you want to share your screen, we can thank Toni again. Okay, great. So next up, we have Josh, who's going to be talking about some of these results in algebraic proof complexity in some more detail. So thanks a lot.
Yeah, thanks very much for the invitation. I'm very happy to be here virtually talking to all of you about this stuff. Yeah, so see if we can get things to go. Oh, and Robert, I can't see the chat. So if people do have clarifying questions in the middle, please do put something in the chat or raise your hand or unmute. But if it's in the chat, Robert, if you could flag me about that.
Yep, no worries.
Great. Yeah, so my main goal for the rest of this session is to get people excited about and talk a little bit more about the details of strengthening the ties between algebraic proof complexity and algebraic circuit complexity. And my vehicle for doing this is going to be to sort of see that a common thread here is thinking about complexity in ideals. So I'll go into more detail on this in a minute, but just to give you some terminology. So we'll always basically have a family of polynomial rings, one for each n, in some number of variables that usually will be growing, say, polynomially with n. And within each of those rings, we'll have a family of ideals, you know, in in Rn. But sometimes I will just say ring or ideal when actually what I mean is a family of rings indexed by n and an ideal, you know, family of ideals indexed by n. And the main question is going to be, given such a family, what can you say about the complexity of all polynomial families that are contained in that ideal? And in particular, can you get lower bounds on all of them? Okay, and where did this come from? So this came from a bunch of different places. It shows up in geometric complexity theory and algebraic natural proofs. And the ones that I will talk about today are in polynomial identity testing, algebraic versus Boolean circuit complexity, and of course, the main theme of this session, algebraic proof complexity. Most of these are not new, but I hope to convince you it's sort of a nice unifying viewpoint in thinking about the relationships between these things and how these things are similar or are different from one another. All right, so just to make sure everyone's on the same page, we're going to start with some basic definitions. Hopefully everyone has seen these before at least once in their life, but maybe if it was a long time ago or you don't remember, hopefully this will be a good refresher. So a ring is a structure. It's a set with addition and multiplication, you know, a 0 that's the additive identity, a 1 that's the multiplicative identity, and it satisfies sort of the axioms you would expect. So addition should be commutative. In this talk, multiplication will also be commutative, except for like one slide. And the big one is multiplication distributes over addition. A bunch
you
of
said it was okay to interrupt. Sorry, I didn't know if are rings closed under specifically addition, multiplication, and that is, we assume that?
Yes, absolutely.
Okay,
yep, they're
great.
closed under addition, multiplication. They have these additions commutative. They're additive inverses, so negative is a thing. There are not necessarily multiplicative inverses, and multiplication distributes over addition. So examples are like the integers, rationals, reals, complex numbers, finite fields, polynomial rings, integers mod n. All right, and an ideal is a subset of a ring that is closed under addition and negation, and is closed under multiplication by arbitrary elements of R. So an ideal, it's like a subring of R, but this second condition is actually much stronger than just being closed under multiplication within itself. It's closed under multiplication by arbitrary elements of R. So sort of once you're in the ideal, no matter what you multiply by in R, you stay in the ideal. Okay, and if we have a finite set, F1 up to Fk, we say that I is generated by this set if it's the smallest ideal that contains those. And in that case, the notation I'll use is this angly brackets notation. And it follows, if you sort of work through the fact that it's closed under addition and negation and multiplication by arbitrary elements of the ring, that if the ideal is generated by these things, then it is precisely the set of things of this form. So if it's generated by F1 up to Fk, your ideal is the set of things of the form sum of Fi Gi, where Gi can be arbitrary elements of R. So some examples of ideals, the ideal generated by a prime P or a number n in the integers just consists of all the multiples of P. You can also, another small example, if you look at the ideal generated by x squared and y in f of xy, doesn't really have a nicer description than this. It's the set of things of the form gx squared plus hy. Okay. And then a coset of an ideal is you take an ideal and you take one element of the ring and you just shift the ideal by that element. So you add that one element to everything in the ideal. And the cosets form a quotient ring. And so this is really sort of the other way to get at ideals is they're the kernels of quotient rings. All right. Right, and so we're mostly going to be talking about ideals within polynomial rings, where they're always finitely generated, again, except for one slide, which I'll mention, and cosets of those. All right, so a little bit more prologue, just a quick primer on algebraic circuit complexity, and this will be useful for other things I'm talking about, but will also give us the first instance where we can talk about complexity and ideals. So an algebraic circuit, for me and for many people, it's a directed acyclic graph. The internal nodes are labeled by plus and times, and the plus gates are really linear combination gates, so you can have coefficients on the things coming into a plus gate, and it sort of computes as you would expect. So a times gate multiplies its inputs. A plus gate here, it's adding its inputs, but again, it's a linear combination. So here we have a -1 on this edge, that gives us this minus here. And they can have multiple inputs, multiple outputs. Things can get reused. Otherwise it's just a circuit. It's just a DAG. And the size of a circuit here is going to be the number of gates. When you get to really low-level classes, you may distinguish between number of gates and number of wires, but we won't be dealing in such low-level classes. All right, so the class VP, for valiance P, is the class of P computable functions, which is polynomial families, such that the nth polynomial in your family has at most poly n variables, at most poly n degree, which is sort of actually a non-trivial restriction, and poly n size algebraic circuits. And the classic example here is like the determinant family. So the n by n determinant has n squared variables, degree n, and poly size circuits with a little bit of work. This follows more or less from Gaussian elimination. And then VNP is supposed to be sort of the algebraic version of NP, although it's more like sharp P, sometimes called the class of P definable functions. So they're families of functions, Fn, where there's another family of functions, Gn, that's in VP, where you can get Fn by summing over all Boolean assignments to some of the variables of your VP family. So this is, you can think of this sum as it's like counting witnesses to an NP problem. But remember, we're here over a field, but we're still only doing the sum over 0, 1. Right, so this is it's like Boolean non-determinism in an algebraic setting. And a classic example here is the permanent. And just to give you the flavor This is one way to express the permanent in this form. So if you look at everything inside this summation, this is expressed as a poly-size algebraic circuit, in fact, of like depth 3 or something like that. And if you look at what it's doing, so I'm summing over Boolean n by n matrices here. This first product here, so these are all Boolean. So each factor here is either 0 or 1. The only way for this first product to be 1 is if this matrix has at most 1, 1 in each row. And then this second one, the only way for this product to be 1 is, or to be non-zero, and then it will be forced to be 1, is if there's at least 1, 1 in each row. So these two together will only multiply to a non-zero thing, and it will be 1 if E is a permutation matrix. And then that permutation matrix tells you which entries to pick out to multiply together in your monomial. Okay. And it's an interesting question in its own right, but also if you're coming from Boolean complexity, Burgosser showed that if NP is not NP poly, then VP is not equal to VNP. And notice in the definitions of VP and VNP, I didn't say anything about the relationship between Fn for different values of n, so it's inherently sort of a non-uniform model. You can talk about uniform versions, but so that's why non-uniformity is showing up here. So if you come from the Boolean complexity world, one thing we can say is, well, this lower bound is sort of formally necessary, right? If you want to prove NP is not contained in P poly, that implies VP not equal VNP. So like, let's start there. It's also more structured, right? These circuits, particularly if you're over something like the rationals, they don't have access to the bits, whereas in Boolean complexity, you would have access to the bits. And so you might say, well, if we can't even prove lower bounds in this more structured model, you know, what hope do we have in the Boolean model? And then in Valiant's original paper where he introduced these, he also argued that actually the issues that arise in the VP versus VNP question are actually capturing some of the core issues that show up in P versus NP. All right, and so this brings us to our first example of complexity in ideals, and this one really is classical. So one distinction I want to make is that in algebraic complexity, we typically consider polynomials symbolically. So for example, even if you're over the integers mod 2, the polynomial x squared minus x, it always takes the value 0 if you evaluate it over anything mod 2. But as a polynomial, it is symbolically different from 0. And so this is actually a different polynomial, even though they're the same function. But in Boolean complexity, we really care about the function. And one way to express this difference, so we saw this in Tony's talk already, is you can translate Boolean operations to algebra. So variables go to variables, negation goes to 1 minus f. So if f is 0, 1 valued, then this switches whether it's 0 or 1, and goes to product. And whatever Boolean function you had over here, if you do this translation, you will get some polynomial here over your field that when you restrict it, when you look at what's happening on 0, 1 inputs, it always gives you 0, 1, and it's the function you started with. Okay, so that seems great. But then why do algebraic lower bounds not give us Boolean lower bounds? Well, it's because this gives you one polynomial that has this property, but there are in fact many polynomials that define the same Boolean function if you look at their restriction to just 0, 1 to the n, even over finite fields. Right, so you might say, well, over finite fields, sort of you can simulate everything in both directions, everything's finite. But you still have this issue that you're considering polynomials symbolically. And so there are many polynomials that give you the same Boolean function. This is just what I said before. And here ideals show up. So we can actually classify in terms of ideals precisely when two polynomials give you the same function, which is when their difference is in this ideal, the ideal generated by xi squared minus xi. Okay, that may not be immediately obvious, although hopefully it doesn't feel implausible if you haven't seen this before, but this is not too hard to show. But the message here is, if you're coming from the algebraic circuit world and you want to say, well, what's the difference between algebraic circuit lower bounds and Boolean circuit lower bounds? Well, if instead of proving an algebraic circuit lower bound, say over a finite field, on a single polynomial family F, you proved it on all polynomials in this coset of an ideal, that would then give you lower bounds on the Boolean function. Okay. So this is the first place where we see, thinking about things in terms of ideals and ideals cosets gives you a very precise relationship between lower bound, in this case, algebraic circuit lower bounds and Boolean circuit lower bounds. All right, so before I come to algebraic proof complexity, I just want to pause for questions. I introduced a lot of things or recalled a lot of things for some people. So yeah, any questions at this point?
So, so just on the previous slide, actually, you said that, that this, so while, you weren't proving it, it should make sense. Can you just give the a brief intuition on why it's specifically that x squared is y minus x of I there for all I?
Yeah, okay, so if they agree on the Boolean cube, then their difference is 0 on the Boolean cube.
Okay.
Right? That's
right.
an if and only if. Okay.
Sure.
All of these functions, these xi squared minus xi, they are 0 on the Boolean cube.
Right.
And let me do the easy direction. If you have something in this ideal, any polynomial in this ideal is 0 on the Boolean cube. Because what does it look like? It looks like a sum of gi's times these things. But if I plug in anything in the Boolean cube, these things become 0. So every summand there becomes 0.
Oh, okay.
So that's the easy direction. The hard direction is the other one that actually follows from the Nostellensatz. But once you have that sort of in hand, it's like a 2-line proof or something.
Okay, cool. Yep, thank you.
Mm-hmm. Right. Other questions? Okay, so let's come back to algebraic proof complexity now. And I am going to be repeating some things that Toni has already said, partially on purpose. Let's pretend like it was totally on purpose. But I'm also going to, I think for most of the things I repeat, I'm going to go into a little bit more depth so that we can start to get a feel for them and start actually thinking about, how do we prove these kind of lower bounds. One thing that I really like, so I didn't start out in proof complexity. I started out much more in algebraic circuit complexity. And one thing I really like about proof complexity is that it gives you a way of measuring the complexity of an individual instance of SAT. You can ask about what's the shortest proof in a given proof system that a given formula is unsatisfiable, right? And that's a number that you get for any one SAT instance. All right, so let's see. Toni already talked a little bit about systems of unsolvable polynomial equations. This arises naturally both in geometric theorem proving and also, as Toni talked about, as a path towards these AC0P Frege lower bounds, which are sort of frustratingly and intriguingly still open, even though we have AC0P circuit lower bounds for almost 35 years now. All right, and just as before, and as we saw in Toni's talk, if you had Boolean equations like the clauses in a CNF, you can translate those into a system of algebraic equations, and then we use the Nostellensatz. So just to recall from Toni's talk again, because now I'm going to phrase it in terms of ideals, a system of polynomial equations has no solutions over an algebraically closed field if and only if there are some other polynomials gi such that the sum of the fi gi is equal to 1. And again, this is syntactically like as a polynomial, as a syntactic polynomial, as a symbolic polynomial. But the other way to say this is precisely that 1 is in the ideal generated by f1 up to fk. Okay. And so now we come to the ideal proof system, which Toni introduced in her papers in 96, 98, and then she and I in 2014 found some nice connections and slightly different, maybe slightly simpler formulation, but the proof system really goes back to her original papers. So this is just a restatement of the Nullstellensatz. And what we're going to do is we're going to introduce new placeholder variables, y1 up to yk, that will take the place of our original equations. So we get a new polynomial that's now in variables x and y. So from any Nullstellensatz linear combination like this, if you just replace the f's by y's, you get a polynomial like this, and this is now just a polynomial and some x's and y's. And so we say such a polynomial is an IPS certificate if when you plug back in the f's for the y's, you get 1. So that's like this, turning this back into this. And also, this polynomial should be in the ideal generated by the yi's, which if you sort of go back through, like, why do we say that? Well, because when we plug in the f's, we want to make sure that the thing we get is in the ideal generated by the f's. And so this is really, I haven't actually said anything about circuits yet, right? This is just a definition for a polynomial and 2 sets of variables to be an IPS certificate. So here's that definition again. And then now you have a polynomial, so you can talk about algebraic complexity in any of the ways that you're used to. So algebraic circuit size, formula size, depth, VNP, whatever you want. The default, we sometimes use algebraic circuit size with no degree bound because that lets us simulate extended Frege. But it's very natural to do it, look at things that have VP IPS certificates and so on. But again, the key thing is, like, use whatever your favorite measure of algebraic complexity is, right? It's just a polynomial. By the way, so Toni mentioned this, but I just want to highlight it now that we're thinking about complexity and ideals, is the cone proof system for semi-algebraic complexity, introduced by Alexeyev, Grigoriev, Hirsch, and Samaret. Where the cone proof system is sort of the circuit version of SOS. And you can ask, for everything that I'm talking about in this talk about complexity and ideals and ideal cosets, what's the analog of that for the cone proof system? So that's a thing I'm interested in, but for people who are interested in semi-algebraic stuff, I'd encourage you to talk about and would be happy to talk with you about. All right, so now I want to tell you a few basic things about IPS and its connections with circuits. But to do that, I have to say one more thing, which is introduce polynomial identity testing. So if you have a circuit class C, an algebraic circuit class C, the polynomial identity testing problem for C is you're given an algebraic circuit from this class, and you're asked, does that circuit compute the zero polynomial? And here I really mean polynomial, not just function, right? So the symbolic zero polynomial. This problem has a randomized algorithm, which is basically evaluated at random points. If your field is not big enough to evaluate it at enough random points, then you're given the circuit, evaluate it over an extension field at enough random points. There are many proofs of this. I'm partial to there's a one-page proof by Dana Moshkovitz from 2010. But yeah, there are many, many proofs of this by now. And in 2004, Cabanetz and Impagliazzo showed that de-randomizing this algorithm implies circuit lower bounds. And in their original proof, it was like either Nexp is not in p-poly or permanent doesn't have small algebraic circuits. And that was simplified so that there was no longer this disjunction by Carmesino, Impagliazzo, Cabanetz, and Kolokolova in 2015. Let's see, and I see in the chat, can you easily check if it computes the zero function? So over a finite field, over a fixed, a constant size finite field, checking if it computes the zero function is co-NP hard. So like if you ask if it computes the zero function over the integers mod 2, that's a co-NP hard problem. So here we're really using the fact that you're given the circuit and you're asked about it as a polynomial, which means you're allowed to evaluate it on extension field, on elements of extension fields. Yeah. All right, so, but we do have an easy randomized algorithm. And that's gonna give us randomized verification for IPS proofs. So the proof systems that Toni was mostly talking about, polynomial calculus, Nullstellensatz, SOS, Frege, they're all line-by-line proof systems, and you can verify them by just checking that each line follows from the previous line. In IPS, that's not the case, because an IPS certificate could just be a circuit, and the condition is on the output polynomial of that circuit. So what we get is, if instead of NP not equal co-NP, implying super polynomial size proofs, as it does for many of the deterministically verifiable proof systems. Here we get, if NP is not in co-MA, then some tautologies require super poly size IPS proofs. And note that if NP is in co-MA, pH collapses. So this is not quite as weak as NP not equal co-NP, but like it's close. And what's the proof here? The proof is Merlin non-deterministically, suppose not. So suppose there are always poly-size IPS proofs. Merlin non-deterministically guesses the poly-size circuit. And then Arthur, using randomness, verifies these two polynomial identity tests. So you're given this circuit, you want to verify it's always 1. That's the same as subtracting 1 from both sides and saying that, this minus 1 is identically 0. And being in the ideal generated by the yi's is the same as saying when you plug in the zeros for the y's, you get the identically 0 polynomial. So these are two instances of PIT, which Arthur can then verify using randomness. Okay. And okay, I swept some things under the rug here. Like if you're over the rationals, what happens if this circuit requires large bit size and so on. If you have big constants or you're over a big field, this proof requires a bit more work. You need at least what I know currently is you need co-AM instead of co-MA. And if you're in characteristic 0, you might need the Riemann hypothesis. But the idea of the proof is somehow, like, this is still the core idea of the proof. Okay, so right, this is one place that polynomial identity testing shows up, and there's an interesting question here about whether this verifying IPS proofs is equivalent in complexity to general PIT. And then another connection, which was sort of one of the big results from my paper with Toni, was super polynomial lower bounds on IPS imply VP not equal VNP. And the way we did this was you show that if you have an unsatisfiable CNF and you translate it into algebraic equations the way that we've talked about, it always has a VNP IPS certificate. Okay. And these 0 here, this just means constant free. But if you don't like thinking about constants, you can drop the zeros everywhere and everything is still true. So let's just assume this key lemma. And if people are interested in the proof, I can maybe talk after offline about it. It's not long, it maybe takes 5 minutes, but I have other things I want to get to here. But let me just walk through a little slowly, assume the key lemma. What's the proof of this theorem? Because this will, again, bring us back to complexity in ideals. So suppose you had a super polynomial lower bound on IPS for proving tautologies. Well, that means that every IPS certificate requires more than polynomial circuit size. But some certificate is in VNP, that's what the lemma says. So that certificate gives you a function in VNP that requires super poly size circuits. One interesting thing about this is we don't know that these certificates have to be VNP complete, right? So we're not using VNP completeness at all here. And there are some interesting questions about, well, what are the complexity of these circuits that we construct in this key lemma and so on. Okay, right, and this was interesting because prior to this, there weren't proof systems known where super poly lower bounds implied circuit lower bounds. Or I should say super poly lower bounds on an arbitrary CNF implied circuit lower bounds. All right, so now how do we get from there to complexity and ideals? Okay, and then we'll talk more about how do we actually prove lower bounds on complexity and ideals and complexity of IPS certificates. All right, so here's our definition of IPS certificate. And one thing you can ask, which we ask because it has a nice answer, is what structure does the set of all IPS certificates have? So you have your fixed system of polynomial equations that's unsatisfiable. You ask about all IPS certificates. Does that have some structure to it? And it does. And this is one of the things that I think that I like about this. You know, if you ask about what structure does the set of all Frege proofs of something have, I mean, surely there are answers, but I don't know of any answer that's as clean as this. So the first condition here, we can actually rephrase in terms of ideals. This is really saying, if you plug in the f's for the y's, you get 1. But plugging in the f's for the y's is the same as modding out by this ideal, where you say you're modding out by yi minus fi of x, right? You're saying this is 0 after I mod out by this. So in other words, after I mod out by this, yi is equal to fi of x. And so what is this? Condition 1 is saying after you do that modding out, you get 1. But that's the same by like the definition of what the quotient ring is, as saying that C is in this coset of this ideal. It's in 1 plus this ideal of yi minus fi's. Okay, so the first condition is about being in a coset of a certain ideal. The second condition is already phrased as being in an ideal. And so the set of IPS certificates is an intersection of these two. And there's a general theorem that the intersection of two cosets of ideals is a coset of an ideal. So the key question for IPS is about the complexity of IPS certificates, i.e. if you want a lower bound, you want a lower bound on all polynomials in this ideal coset. Okay. And now, another connection here with PIT, and this is the one slide where things get non-commutative. After our paper in 2015, Lee, Samaret, and Wang showed that Frege, the classic Boolean proof system, is actually quasi-polynomially equivalent to a non-commutative formula version of IPS. When you're given the clauses of your CNF, the Boolean axioms, xi squared minus xi, and commutativity axioms. So we're in a non-commutative ring, but you're allowed to commute things, but you have to keep track of when things commute. Like that costs you something to commute things. And the main idea of their proof was to take the Raj-Shpilka non-commutative formula polynomial identity testing algorithm, deterministic polytime. You could use that to verify non-commutative formula IPS proofs. And the main idea of the LTW proof is to show that the Raj-Shpilka PIT algorithm can be formalized in Frege. So Frege can essentially simulate that algorithm, and therefore Frege can verify non-commutative formula IPS proofs. And this is one of these instances that Toni mentioned briefly of, what's the proof complexity of polynomial identity testing? Okay, and in this case, they showed that it could be done efficiently, and that's how you get this equivalence, which I think is also notable because Frege is really a syntactic, line-by-line Boolean proof system, and non-commutative formula IPS arguably is really much more semantic, right? You still have this notion of a non-commutative polynomial is an IPS certificate. It can be computed however you like by any non-commutative formula. And so this is interesting to me, partially because it's an equivalence between a syntactic system and a semantic system. Now, even in this non-commutative setting, it's still the case that the set of IPS certificates is an ideal coset, as it was before. But in the non-commutative setting, ideals don't have to be finitely generated anymore. And so, okay, what does that tell us? I don't know. I've had several conversations with people over the years. The jury is certainly still out on that. But it's an interesting thing to think about when you think about, what's the difference between, say, this and general IPS is sort of, what's the difference between the non-commutative ideal cosets that arise here and the commutative ideal cosets that arise for general IPS. All right. So that was sort of the setup for algebraic proof complexity. I want to do one more quick connection between PIT and complexity and ideals, and then we'll talk about, in the last probably 10 minutes or so, how we actually prove lower bounds on complexity and ideals or prove lower bounds on IPS. All right, so one approach to polynomial identity testing is what's called hitting set generators. So a hitting set generator for complexity class C is a polynomial map that takes m parameters and outputs n polynomials, such that any non-zero function in your class is also non-zero when you compose it with G. Okay, so if you're over an infinite field, this is the same as saying that f is non-zero on the image of G. Okay, so the idea is here, the image of G is a hitting set in the usual sense, if you've seen those. But here you can talk about G purely symbolically as a polynomial map. Okay. This is really an approach to PIT using lower bounds on ideals. So the set of polynomials such that when you compose them with G, you get 0 is an ideal. Okay, and we can do the proof quickly. If you have two polynomials that compose with G give you 0, you take their linear combination and compose it with G. Well, what does that do? That's the same as taking the linear combination of the two compositions separately. Each of those were 0, so this is still 0. And then we need to be able to multiply by any polynomial. So if f composed with G is 0, you multiply by any polynomial, similar trick. It's the same as composing those two polynomials with our generator first and then multiplying them. But f composed with G was 0, so this is still 0. Okay, and then if you just trace through, this is exactly the set of things that when composed with G are 0, we want things that when composed with G are not 0. What you get is G is a hitting set generator for this class, if and only if you have a C lower bound on all polynomials in this ideal. In other words, there are no non-zero polynomials in this ideal that are also in this circuit class. Okay. All right. So now I want to come to sort of the crux of the matter. How is, when we talk about circuit lower bounds, we talk about lower bounds on a complexity class, which is also a collection of families of polynomials. And here we have ideals, which are collections of families of polynomials. So how is this different than what we normally think about? And how do we use this to prove lower bounds? But before I get there, again, I think now is a good time to pause for questions. So any questions at this point? Okay. All right, so we're going to talk about complexity in complexity classes versus complexity in ideals. And to do this, we need to talk about not just algebraic circuits, but algebraic circuit reductions. So here, if I want to reduce to a polynomial f by an algebraic circuit, I allow myself algebraic circuits as before, but I also allow f gates. So this, these gates compute as you would expect. The f gate, well, f is some polynomial. In this case, it takes two inputs, and it just takes those inputs and applies them, and then it continues on its way through the circuit. Okay, so we defined C superscript f of G to be the minimum circuit size to compute G, where you have linear combination times and f gates. And then if you have two families of polynomials, Gn and Fn, we say G is a C reduction of f if you can compute Gn in poly n size by reducing to f's that also are, only poly n bigger in terms of their index here. And then we define the C degree of a polynomial family as just the equivalence class under this notion of reduction. C degree, it functions a lot like many 1 degree or Turing degree in the Boolean world. Just like in the Boolean world, you have Ladner's theorem. In the algebraic world, Burgesser proved an analog of that, which is if f is strictly below G, meaning if C reduces to G but not vice versa, then in between those two, any countable poset you want embeds in the poset of C degrees in between them. This is sort of a souped up version of Ladner's theorem, but we also know this. I think it's a result of Schoening in the Boolean case. All right. So now we come to what's the difference between lower bounds on complexity classes versus lower bounds on ideals? Well, let's look at VP versus VNP. So to separate these, it suffices to show a lower bound on one polynomial in VNP, right? To show that there's one polynomial in VNP that's not in VP. But in all these cases where we were talking about complexity in ideals or ideal cosets, we want to know a lower bound on every polynomial in the ideal, right? So this is sort of the key difference. And then you can start to ask, well, how could we do that? So in complexity classes, we're used to, they often have complete problems. So if you want to find one polynomial that's in VNP but not VP, without loss of generality, you can look at the VNP complete, pick your favorite VNP complete polynomial. And the question is, could you do a similar thing for ideals? Only now we want a lower bound on every polynomial in the ideal. So instead of the hardest problems, which is what we have when we have completeness, we want the easiest problems. You would like there to be a unique easiest problem in the ideal so that a lower bound on that is a lower bound on everything in the ideal. And so you get this question, do ideals have minimal C degrees, the easiest problem in this ideal? And okay, in general, this is open, but some things are known, and some of those things that are known will actually give us lower bounds on ideals and on IPS. So the simplest kind of ideal is a principal ideal, which means it's generated by a single element. So suppose you have a family of those. What is this ideal? Well, it's the multiples of this generator. It's literally things of the form, G times H. Okay, and so now when you're talking about complexity in this ideal, you're talking about relating the complexity of a polynomial with the complexity of its multiples, or relating the complexity of its multiples to the complexity of their factors. And so under the guise of thinking about factorization, Kaltofen and Bergeser proved that there is a relation, namely if F is a multiple of G, then the complexity of G is at most polynomial in the complexity of F. And also this annoying factor here of, if G appears to a high power, that also shows up. When that high power is small, this is not just a bound on the circuit complexity, it's actually a reduction. So you can compute the factor from the original polynomial. And there was a question of, can you get rid of this dependence on E? And Bergeser showed you could if you use border or approximative complexity instead of ordinary circuit complexity. But then there's this open conjecture, the factor conjecture, which has several forms, but let's say for this talk, we'll say it's that, if G and F both have polynomial degree and G is a factor of F, then GC reduces to F. Okay, so this is almost true. It's true sort of up to border complexity, and the factor conjecture is that you can get a similar thing without this border complexity issue. Okay, so Forbes, Spielkot, Samaret, and Wigderson leverage this, or this idea of lower bounds on principal ideals. They weren't thinking about it, I guess, well, I don't know, but they didn't phrase it in this language, but this is what they did to get some lower bounds on IPS. So they have a lemma which says, suppose you have an unsatisfiable system of polynomial equations, but when you drop this equation, F, from your system, it becomes satisfiable. Then from any IPS certificate of unsatisfiability here, you can get a circuit that's essentially the same size that gives you a non-zero thing in the principal ideal of F, i.e. a multiple of F. Let's see, do I have time? Yeah, great. So the proof is not too difficult. The idea is if I plugged in F here, because this is an IPS certificate, I should get 1. When I plug in 0 here, I necessarily, therefore, get something in the ideal generated by F. So I get a multiple of F. How do I know it's something non-zero? Well, because if it were 0, that would say this IPS certificate really doesn't depend on F at all, but it really has to, because when you drop F here, it switches from being unsatisfiable to satisfiable. So their strategy here, they called it lower bounds for multiples. And from this strategy, they get exponential lower bounds on restricted systems of IPS for these polynomials. And this gets back to I think it was Robert's question. So for depth 3 powering circuits, IPS, here they have the Boolean axioms. They say the sum of your variables is some m, and the product is 1. Well, the only way for the product to be 1, if they're Boolean, is for all of them to be 1. So as long as m is different than the number of variables, then this is unsatisfiable. Okay. Right, so they use this strategy of lower bound for multiples to get that, and then sort of a similar thing is happening here, but now for read once algebraic branching programs. Okay, so from lower bounds on principal ideals, you get some lower bounds on restricted versions of IPS. And then the other strategy they introduce in their paper is what they call functional lower bounds. But in the context of this talk, we recognize these as lower bounds on a coset of this Boolean ideal. So what they say is, suppose you have a system of polynomial equations that looks like this. There's one polynomial, and then the Boolean axioms. And suppose it's unsatisfiable. If you look at the polynomials that agree with 1 over f on the Boolean cube, right? And this is unsatisfiable, so f indeed is not 0 on the Boolean cube. If you get a lower bound on every such polynomial that agrees with 1 over f on the Boolean cube, you get a lower bound on IPS. Okay, but what is the set of polynomials that agree with this function on the Boolean cube? It's precisely a coset of this Boolean ideal. Okay. So they call these functional lower bounds. In the context of this talk, we would call them lower bounds on Boolean ideal cosets. And from that, they get lower bounds on things like this. So again, they have some Boolean axioms, and they have one additional thing, which is sort of I guess in this case, it's more like an inner product thing, but it's sort of knapsack-like. Okay, and now we come to the very recent exciting result, which is constant depth IPS lower bounds for arbitrary constant depth circuits. So in 2018, when I started sort of thinking about this viewpoint, I gave a talk on this, and I made a conjecture, which was, here's an interesting ideal that is generated by a bunch of things. It's not principal, but I think it should have a minimum C degree, which is you look at the n over 2 by n over 2 minors of an n by n matrix. And the conjecture was that everything in that ideal should be able to compute a determinant. So the determinant should be the unique minimum C degree of this ideal. And just last year, Andrews and Forbes proved that this conjecture is true, and in a very strong way. Okay, they had to use border reductions, but like we've seen that before in the context of Burgesser's results on factorization. But aside from this border, they showed that this is even true for depth 3 C reductions, meaning some large determinant reduces by a depth 3 circuit to arbitrary things in this ideal. Okay, and then they leveraged the very exciting result of constant depth algebraic circuit lower bounds that's appearing in this conference, but many people have already seen it online because of the archive. That in particular, the determinant requires large constant depth algebraic circuits. So then Andrews and Forbes sort of put these two together, and they looked at this set of equations that Toni mentioned, and got constant depth IPS lower bounds. So you have two matrices of variables, x and y. You have the equations determinant of x is 0, x times y is the identity, and all the variables are Boolean. And then they show, using this lower bound for multiples trick, okay, you get a multiple of det, and from a multiple of det, that's in this ideal, you get a depth 3 reduction to an actual determinant. Determinant requires large constant depth algebraic circuits. And so, yeah, that's all very exciting. And you see kind of how these complexity and ideals have been showing up in the background of these things, whether or not people have been using it explicitly. Yeah, Robert, I know I have just a couple minutes left. Yeah, so I just want to end with some open questions. There are lots of open questions on complexity in ideals in general, and also on IPS, and I will highlight some of both. So one question is, if you have an ideal or a coset of an ideal, must it have a unique minimum C degree? Surely this is not the case at this level of generality, but it'd be nice to actually have an example. If it doesn't have to be unique, could we still say something like, well, there have to be only finitely many, right? The motivation for a unique minimum C degree was that, okay, without loss of generality, prove a lower bound on that one. Well, if there are only finitely many, then you still only have a job of proving finitely many lower bounds, and that would give you lower bounds on everything in your ideal. The flip side of this is, do they have to have any minimal C degree? Or could you have like, an infinite descending chain that just goes down and down and down, and there's no minimal degree? And the really, depending on your viewpoint, either frustrating or tantalizing thing here is these are open even for ideals generated by just 2 elements. So for 1 element, we have all these results on factorization for principal ideals. But even for 2 elements, all these questions are wide open. And 2 elements is like very far from the general case. So in general, if you have n variables, the maximum number of generators of an ideal in degree n is like the n plus first level of the Grochow primitive recursive hierarchy. And just to give you, and that's tight, like there exist ideals that need that many generators. And just to give you a sense, the 4th level of this hierarchy, I think, is already all towers of exponentials of fixed finite height. And each level you add a layer of primitive recursive. So this is huge, but we don't even know these things for 2 generated ideals. Okay, and then I will end with IPS questions. So this is one Toni already asked, but it's worth highlighting again at the end of the session here. Get an IPS lower bound on the translation of Boolean tautologies. All the other lower bounds we saw were for nice algebraic things. But we really want to know how this relates back to SAT solving. You can also ask, just like Lee Samaret and Wang did for the Raj-Spilka PIT algorithm, what's the proof complexity of formalizing other PIT algorithms, and what consequences does that have? And then the other one, which is interesting, is if IPS could be simulated by any deterministically verifiable proof system, does that imply some de-randomization of PIT? Right? Verifying IPS looks like an almost general PIT problem, but we don't know it's fully general. But like even super powerful systems like ZFC, we don't know if they simulate IPS. And for all we know, that implies some de-randomization of PIT. All right, so I will leave it there, and I'm happy to take questions and stick around during the break if people want to chat. Thanks.
All right, amazing. Thank you very much. Yeah, are there any questions for Josh? Feel free to unmute and ask, or ask in the chat. I can ask a question first of all. So, so the result that says that non-commutative formula IPS is the same as Frege that uses this known PIT. Mm-hmm. It seems like if you said like if we could de-randomize commutative formula identity testing, and then also maybe prove that in formula in Frege, mm-hmm. that would imply some kind of surprising result about the use of these commutator axioms, wouldn't it?
Yes, that's right. So in Toni and my paper, we said something fairly general, like if you can formalize, if you could prove, if you have like PIT that you can prove in a given proof system like Frege, then that proof system can, like, say you can prove PIT for a circuit class C in Frege, then Frege simulates C IPS. Right. And so, for example, if Frege could prove general PIT, then that would in particular imply like Frege and extended Frege are the same. So I think that would be surprising. But it's very interesting to ask things like, does AC0P Frege, can that prove bounded depth PIT, for example? Yeah.
Right. Cool.
Mm-hmm.
Any other questions? Okay. Well, yeah, let's thank Josh and Toni again for the lovely talks. And I'd just like to say that, yeah, these are being recorded, so they'll be posted available later. And then I'd also like to say a couple of announcements. So first of all, we'll have another session later this afternoon with Sam Buss and Neil Thoppen, who are both attending here. And the other thing I'd like to announce is if you would like to, the Fox would like everybody, if they're interested, to use the Gather Town to socialize now or at the break. So I'm just going to drop a link to that in the chat there. So yeah, thanks a lot, everybody. I guess we can stop recording.